So, imagine tearing apart two completely different engines.
Yeah.
Like one is electric and the other is combustion.
Right, so fundamentally different physics, different supply chains, the work.
Exactly. They run on entirely different operating principles.
Yeah.
But then, imagine you looking really closely at the engineering schematics, and you realize that mathematically, they are generating horsepower using the exact same underlying formula.
Which, sounds impossible.
It does. But that is exactly what is happening right now in the world of variance estimation for complex survey designs.
Yeah.
And for those of you listening who are, deep in the trenches of data science or machine learning or applied math, you expect architectural choices to matter.
Oh, absolutely.
If you build a pipeline with massive cross-dependencies, it really shouldn't produce the exact same algebraic footprint as, say, a pipeline built on strict isolated independence.
But it does, or, well, it can.
Yeah, and today we're pulling apart Matthias von Davier's 2026 paper. It's called Effective Degrees of Freedom for Balanced Repeated Replication and Paired Jackknife Variance Estimates, a unified approach via stratum contrasts. And von Davier shows exactly that kind of mathematical sleight of hand.
It's a fascinating read.
It really is. And even more importantly, we are going to see how this hidden structural equivalence dictates whether your model's degrees of freedom are actually robust or if, under the right conditions, they mathematically collapse all the way down to just a single degree of freedom.
Yeah, the premise is entirely counterintuitive. I mean, we are trained to believe that structural divergence at the input layer guarantees mechanical divergence at the output layer.
Right.
But the paper takes two titans of variance estimation balanced repeated replication, which we generally call BRR, and the Jackknife, and it proves a unified mathematical framework for them.
So the goal is to show how these two completely structurally different variance estimators just collapse into the exact same algebraic form.
Exactly. And finding that unified form is what actually unlocks a single unified Welch-Satterthwaite degrees of freedom calculation.
Okay, let's unpack this. Because before we dig into the unification, we should probably define the sandbox we're playing in. What are the baseline parameters for the designs von Davier is analyzing here?
Sure. So we are operating in the realm of stratified sampling designs.
Yeah.
Specifically, we're looking at designs where we have exactly two primary sampling units, or PSUs, per stratum.
So if we have big H strata, we have 2 times H total PSUs.
You got it. And the overarching objective is to estimate the variance of a population total estimator, which we'll just call T-that.
Okay, got it. So to appreciate the sheer elegance of the unifying formula here, we really need to sit with how fundamentally different the construction of these two replication methods actually are.
Oh, yeah, they are night and day.
Let's start with the Jackknife, specifically Jackknife repeated replication, or JRR, for this 2 PSU design. The construction here is, highly intuitive if you've ever written a script for leave one out cross-validation.
Right, because the mechanics of the Jackknife are built entirely on isolated perturbation. You basically create replicates by deleting one PSU at a time and then adjusting the weights of the remaining units to compensate.
Let's visualize that real quick with a tiny hypothetical survey just to ground it. Imagine you have an urban stratum and a rural stratum, and they each have 2 clinics.
Okay, perfect. So in the Jackknife, for your first replicate, you drop urban clinic 1, and then you double the statistical weight of urban clinic 2.
And the rural clinic.
The rural clinic 1 and 2 remain completely untouched. Then, for the next replicate, you drop urban clinic 2, and you double the weight of urban clinic 1.
And because you do this for every single PSU across all H strata, you end up with exactly 2 times H replicates.
Exactly. And the dependency structure, or really the lack of it, is the defining feature here.
Right, because within a single stratum, the 2 replicate deviations are perfectly negatively correlated.
Yes, exactly perfectly. If dropping unit 1 pushes your total estimate up by a specific amount, dropping unit 2 pushes it down by that exact same amount. But across different strata, the contributions are entirely independent by construction.
Because what happens when you manipulate the weights in the urban stratum has absolutely zero mathematical correlation with the replicate operations happening in the rural stratum.
Right. It's clean, isolated perturbation.
Clean and isolated. But then we look at balanced repeated replication. And this is where things get computationally aggressive, to put it mildly.
Yeah, aggressive is a good word for it.
Because instead of deleting one unit at a time and keeping everything else static, BRR perturbs everything, everywhere, all at once.
It really does. Rather than walking through strata sequentially, BRR uses a Hadamard matrix of order R to systematically select one PSU from every single stratum simultaneously for each replicate.
and a Hadamard matrix is essentially a perfectly balanced square grid of plus ones and minus one.
Okay. Exactly. But it's designed with a very specific, crucial property. Every column is mathematically orthogonal to every other column.
Wait, so how does that matrix actually map to the survey weights in practice?
Well, you take the first H columns of that Hadamard matrix, so one for each stratum, and for any given replicate, which corresponds to a row, let's call it R, in the matrix, you look at the entry. Let's call that alpha sub RH.
Okay, and that entry is either plus one or minus one.
Right. If it's plus one, you double the weight of unit one in that stratum and you zero out unit two. If it's minus one, you do the exact reverse. And you execute this rule across all H strata at the exact same time.
Okay, so this is where the tension in the paper really hits me, because BRR replicates shared data across all strata simultaneously. The replicate estimates themselves are heavily correlated.
No, massively correlated.
You don't have that clean, isolated independence between the urban and rural strata anymore. Every replicate is a massive soup of overlapping perturbations.
Right, it's all blended together. So how can a method with heavily correlated replicates like BRR and a method built on independent stratum-level deletions like Jackknife possibly be reconciled? I mean, they seem fundamentally incompatible.
Well, you have the BRR variance estimator on one side, summing the squared deviations of highly correlated replicates, and you have the Jackknife variance estimator on the other, summing the squared deviations of isolated, independent paired replicates.
Right.
The central revelation of von Davier's paper is that both of these estimators reduce algebraically to the exact same simple expression.
Wait, really?
Yes. They both evaluate to the sum from h equals 1 to h of d sub h squared.
Where d sub h is the within stratum contrast. To put a formula to it for everyone, d sub h equals the weight of unit 1 times the value of unit 1 minus the weight of unit 2 times the value of unit 2. It's literally just the difference between the weighted observations of the two units in that specific stratum. Exactly. Regardless of the massive correlation across the R replicates in BRR, or the two H replicates in Jackknife, the final variance estimator is just a sum of independent stratum-specific components, the sum of d sub h squared.
Okay, for the Jackknife, the path to the sum of d sub h squared feels really obvious. You isolate a stratum, you calculate the squared deviation, it resolves to d sub h squared, and you just sum them up across the strata.
Because the independence is baked in from the start.
Right. But for BRR, wait, if you were squaring a massive sum of replicates across all strata simultaneously, wouldn't that create an absolute nightmare of cross-product terms? I mean, how do you not drown in covariance noise?
Let's trace the math, because the way BRR sheds its complex cross-stratum dependencies is the core mathematical engine of this whole method. We need to look at the deviation for a single BRR replicate R.
Okay.
That deviation is the sum across all strata of the Hadamard indicator alpha sub RH multiplied by the stratum contrast d sub h.
So the sum of alpha sub RH times d sub h.
Yes. Now, the variance estimator requires us to square that deviation. And, you know, when you square a sum like that, you don't just get the squared individual terms, you get the full polynomial expansion.
Right, you get the cross products.
Exactly. You get a double sum over the strata. Let's index them as h and k of alpha sub RH times alpha sub RK times d sub h times d sub k.
Which is exactly the nightmare scenario I was talking about.
Yeah.
You get the clean variance terms where h equals k, sure.
Yeah.
But you also generate this massive dense web of covariance terms where h does not equal k, like the urban-rural cross-contamination.
Right, and what's fascinating here is that if you stopped at a single replicate, it would be an unusable mess of cross-stratum noise. But the BRR variance estimator doesn't stop there.
Because it sums these squared deviations over all our replicates.
Exactly. The mathematical trick happens when you reverse the order of summation. Instead of summing over the strata first, you sum over R the replicates first. So you end up summing the product of the Hadamard matrix entries, the sum from R equals 1 to R of alpha sub RH times alpha sub RK. Oh, wow. And because we're using a Hadamard matrix, we know the columns are orthogonal.
Yes. By the strict definition of orthogonality, the dot product of any two different columns in that matrix is exactly 0. So for all those messy covariance terms where h is not equal to k, that entire sum across the R evaluates to 0.
That's incredible.
Every single cross-stratum covariance term is utterly annihilated by the matrix structure. The only terms that survive the summation are the variance terms where h equals k.
Because in that case, you're just summing alpha sub RH squared.
Right, which is just 1 summed R times, giving you R.
So the matrix is doing something very similar to like destructive interference in wave physics, like how noise-canceling headphones work.
Oh, that is a highly accurate way to conceptualize it. I love that.
Right, because you have this overlapping correlated noise of the cross-stratum data being generated by the BRR selection process.
Yeah.
But because the Hadamard matrix is perfectly balanced by design, that noise is engineered to be exactly out of phase with itself across the R replicates.
And when you aggregate them, the noise perfectly cancels itself out through destructive interference, leaving behind only the pure independent signal, the specific stratum contrast, d sub h squared.
Exactly. The complex dependencies of the replicates are basically merely a computational scaffold. Once you sum across the balanced design, the scaffold just collapses, leaving you with R times the sum of d sub h squared.
And then the standard BRR estimator just divides that total by R.
Right, and you are left with simply the sum of d sub h squared. You arrive at the exact same foundational DNA as the Jackknife.
Okay, I buy that. I buy that the matrix annihilates the noise in standard BRR. We have established this beautiful base mathematical equivalence. But any applied statistician listening is immediately going to ask about robustness.
Naturally.
Because this mathematical cancellation assumes we are safely dropping and doubling units by assigning weights of 0 and 2. But what happens when we hit a small subpopulation where, dropping a unit means deleting the entire demographic from the model for that replication?
Yeah, that is the practical wall you hit with standard BRR and JRR. If you zero out the only units representing a small domain in a particular replicate, your estimate for that subpopulation becomes mathematically undefined or wildly unstable.
Right.
And this is exactly why Robert Fay introduced a perturbation factor, which we denote as epsilon.
Phase method.
Exactly. Instead of using a harsh zero and double weighting scheme, Fay's method softens the perturbation. So you assign one unit a weight of 1 plus epsilon times the original weight, and the other gets 1 minus epsilon times the weight.
And epsilon's usually what, 0.5?
Typically 0.5, yeah, though you might see practitioners use 0.3 or 0.7, depending on how they need to balance computational stability against the magnitude of the replicate deviations.
But the critical outcome is that every single unit retains a positive non-zero weight in every single replicate.
Precise.
But wait, if Fay's method artificially keeps units alive with a fractional weight, doesn't that leave behind mathematical residue? Like if we are fundamentally changing the weight so they aren't zero, we're changing the actual replicate deviations.
Right, you're not getting a clean zero.
So you can't just wave a wand and say the cross terms still cancel perfectly. Doesn't injecting this epsilon factor into every calculation completely wreck the sum of d sub h squared unification?
Well, it's not magic, it's algebra. Let's look at where the epsilon sits in the equation for Fay BRR. The replicate deviate from the full sample estimate changes. Because you are only perturbing by a fraction epsilon rather than a full 100%, the deviation is no longer just the sum of alpha times d.
Okay.
It becomes epsilon times the sum of alpha times d. The epsilon is just a constant that simply factors out linearly.
Oh, I see. So the deviation itself is just scaled by epsilon, meaning when you square that deviation to calculate the variance, you basically get an epsilon squared term sitting out front of the polynomial expansion we discussed earlier.
Yes. And the brilliance of Fay's method is that the variance estimator formula itself is modified to account for this. The Fay BRR estimator introduces a scaling factor of 1 over epsilon squared times r, rather than just 1 over r. So you have a 1 over epsilon squared built into the estimator formula, and you have an epsilon squared being generated by the squared deviations. They completely cancel out.
Wow.
The orthogonality of the Hadamard matrix still destroys all the cross terms, and you are left once again with exactly the sum of d sub h squared.
Okay, so that's Fay BRR. Does the paired jackknife handle the perturbation just as cleanly?
The mechanism is identical. For the paired jackknife with Fay's method, your single stratum deviations are epsilon times d sub h and negative epsilon times d sub h, square them, and each becomes epsilon squared times d sub h squared.
Okay, meaning it's...
The Fay jackknife variance formula explicitly uses a scaling factor of 1 over 2 times epsilon squared. You add the two squared deviations together to get 2 epsilon squared d sub h squared.
And then you divide by 2 epsilon squared.
Exactly, and everything cancels except the d sub h squared. Sum over your h strata, and you are right back to the sum of d sub h squared.
So what does this all mean? Fay's method gives us a vital computational upgrade stability for small domains without altering the fundamental independent structure of the stratum contrasts at all.
Not even a little bit.
Whether your epsilon is 0.5, 0.3, or 0.99, the structural equivalence is completely invariant.
And this invariance is the critical bridge in the paper, because von Davier definitively proves that both estimators, whether standard or Fay adjusted, reduce to a sum of independent squared stratum-level components, d sub h squared. And because of that, we now possess the exact mathematical ingredients required for the Welch-Satterthwaite approximation.
Which is perfect, because let's transition to why we actually care about getting to the sum of d sub h squared. In applied work, calculating the variance is rarely the end goal.
Yeah, right. It's just a stepping stone.
We want to construct a confidence interval for our total estimate, t hat. So we assume t hat is approximately normal, and we assume our variance estimator, v hat, is approximately a scaled chi-squared random variable. But to utilize the t-distribution to build that confidence interval, we absolutely need to calculate the effective degrees of freedom, Nu.
Exactly. And estimating those degrees of freedom requires understanding the variance of the variance estimator itself over repeated samples.
Okay.
We know our variance estimator v hat equals the sum of d sub h squared. Therefore, the variance of v hat is the sum of the variances of those d sub h squared terms. And the variance of a squared term requires us to look at the fourth moments.
Right.
Assuming the expected value of d sub h is 0, the variance of d sub h squared relies heavily on the expected value of d sub h to the fourth power.
The classic fourth moment problem.
Yeah.
I mean, calculating higher order moments from sample data is notoriously noisy.
It is intensely noisy. So to make this mathematically tractable, we make a distributional assumption. If we assume that within each stratum, the observations are approximately normal, or at least that we have sufficient sample sizes for central limit theorem effects to take hold, we can approximate d sub h squared as being proportional to a chi-squared distribution with 1 degree of freedom.
And under that specific normal theory assumption, the variance of d sub h squared simplifies beautifully to 2 times sigma sub h to the fourth, where sigma sub h squared is the true variance within stratum h.
Spot on.
And here's where it gets really interesting. Von Davier doesn't just plug this into the textbook Satterthwaite approximation. He leverages his own prior 2026 work on a bias-corrected Welch-Satterthwaite equation to give us the final unified formula for the estimated degrees of freedom, nu hat.
Right, because the standard Satterthwaite equation would give you the square of the sum of d sub h squared divided by the sum of d sub h to the fourth. Von Davier's bias-corrected version provides a much more precise estimation for this specific application.
What's the unified formula?
It is. Nu hat equals 3 times the square of the sum of d sub h squared divided by the sum of d sub h to the fourth minus 2.
Let me state that again just so the architecture is perfectly clear. Nu hat equals 3 times the square of the sum of d sub h squared divided by the sum of d sub h to the fourth minus 2.
Yes.
It is incredibly elegant. But, looking at that formula brings up a very practical coding question for me.
Let's hear it.
If I'm building this pipeline, I already have my massive matrix of replicate estimates. I have the raw deviations for each replicate already calculated. Why can't I just bypass this whole extraction process, compute the variance of those raw replicates, and plug those raw replicate deviations directly into the Satterthwaite equation to save compute time?
If we connect this to the bigger picture, doing that would completely undermine the fundamental mathematical requirement of the Satterthwaite equation.
Wait, really?
You cannot bypass extracting the stratum contrasts. The Satterthwaite approximation mathematically demands independent random variables in the denominator. Let's look at what happens if you use the replicates directly, starting with the Jackknife.
Okay.
You have 2 h replicates. If you plug the squared deviations from those 2 h replicates directly into the denominator, you are functionally using d sub h squared twice for every single stratum.
Because there are 2 replicates per stratum, so you are artificially duplicating your variance components.
Exactly. You are introducing heavily correlated variance components into a formula that explicitly demands independent components. You are double counting your denominator, which artificially deflates your calculated degrees of freedom.
Wow. And for BRR, the trap must be even worse.
The trap with BRR is incredibly subtle, but yes, it's worse. As we established earlier, the raw BRR replicate deviations are linear combinations of all the within-stratum contrasts. Every replicate contains data from every stratum.
Right, the soup.
Exactly. They are massively correlated with one another. The Satterthwaite equation will just fail. The BRR deviations only become independent after you square them and sum them across the balanced Hadamard design, which is what yields the independent d sub h squared terms.
Okay, so the pipeline workflow is completely non-negotiable. You cannot use the replicate outputs directly for degrees of freedom calculations. You must go back to the source. You
Yes.
have to use the known unit weights and the sample values to compute the d sub h components directly for each stratum using the formula. You compute those h-independent contrast values, and you plug those into von Davier's bias-corrected equation.
That is the mandatory operational protocol. You must extract the stratum-level DNA first. Only then can you calculate the degrees of freedom accurately.
I mean, it is a phenomenal synthesis of two completely different approaches. Regardless of whether your pipeline utilizes the computationally intense, fully perturbed architecture of BRR or the isolated iterative deletion method of the Jackknife, the variance estimators share the exact same stratum-level DNA.
They do.
And this unified framework justifies a single, unified algorithmic approach to calculating your degrees of freedom.
We should probably add a very important practical reality check regarding the output of that final equation, though.
Definitely.
Because the Satterthwaite approximation is actively accounting for variance heterogeneity across your various strata, your calculated effective degrees of freedom, nu hat, is almost always going to be less than your total number of strata, h.
Right.
In real-world data, it is often much less.
It's not just a theoretical h minus some tiny negligible penalty.
Yeah.
The heterogeneity of variance actively degrades the mathematical information content of your sample. Which actually leads me to a final thought for you to mull over as you review your own modeling architectures.
Yeah, the extremes here are wild.
Because the paper points out a fascinating and honestly somewhat terrifying mathematical limit. In extreme cases of variance skew across strata, say, where a few strata contain massive variance while the rest are near zero, your effective degrees of freedom can plummet all the way down to 1.
Down to 1.
Just 1. Think about the implications of that for a moment. You could design an incredibly robust, multi-strata, highly balanced survey. You could run a massive BRR with thousands of Hadamard rows, perturbing weights with absolute precision.
Spending all that compute.
Exactly. You could feel entirely secure in the structural complexity and computational power of your pipeline. But if the variance within the data itself is violently skewed, all of that brilliant architecture mathematically collapses down to a single degree of freedom.
It's sobering.
So the question is, how does that underlying mathematical fragility fundamentally change your confidence in the confidence intervals you're presenting to your stakeholders tomorrow? We like to think that complex computational structures guarantee robust results. But sometimes the deepest complexity is just a scaffold, hiding a very simple and potentially very fragile foundation.